All right, welcome everyone to week 11 of AI612. So this week we are going to talk about medical images, which is one of the most popular modalities of healthcare healthcare data. So far we've studied structured data set before project number 1, and then after that we briefly took a look at the medical text, and the project number 2 is actually based on medical text. By the way, is there any question regarding project number 2 besides the one on ClassSum? So I'm going to answer, or myself or the TAs are going to answer questions on ClassSum after this. But generally, any question regarding project number 2? Okay. Question from Sorrow. I extracted the labels and just used them to check the AUPROC in ROC metric while considering the label themselves as prediction, but I got error for AUPRC macro and ROC macro. Therefore, I wonder what is the right way to compute those metrics without having error. Well, actually, Sorrow, without actually, looking at the error messages, I probably don't know what the cause of the error is. Maybe you can share that on ClassSum. Usually, what you should do is you should have a let's see. So AUPRC and ARC are actually they are for evaluating binary classifier, but what we have in the project number 2 is multi-label classification. So I'm not sure if you can directly use average precision and ARC function as is, because what you are trying to input to those functions or those APIs is a matrix. So the rows would be different samples, and the columns would be different classes. But I'm pretty sure that AUPRC and ARC, those APIs are expecting for you to provide a one-dimensional vector. So just ones and zeros just a single row or single dimension of ones and zeros, because it's a binary classification. So it's just different samples of different outputs, and that's it. So there are no multiple columns for different classes. So I think that is probably the reason for the cause of the error. Is that correct? Okay, so yeah, if that is correct, then you should find a way to calculate with a matrix input. Let's see. Micro AUROC scikit-learn. Macro. I guess the function sklearn.metrics.roc_AUC_score does receive or does accept matrix formed input. Yeah, it does actually. So it does, but there is another argument named average where you can specify if you want to use macro or micro or samples or weighted. I think that's where you need to play around with. But I guess the good news is that the ROC AUC score, that API does support multi-class classification or multi-label classification. So no need to come up with your own API. 이재원님의 질문은 HADMID들 중에 ICD9 코드는 있지만 노트 이벤트의 카테고리와 디스크립션이 주어진 조건을 만족하는 텍스트가 없는 애들은 어트라피아 등 아니면 제가 알아서 패딩합니다. 이런 공중적이동 데이터의 개수가 있는 유니크한 HDMID 정했는지 아니면 그런 질문이 클래스홈에 있었던 것 같은데요. 제가 뭐라고 답을 했는지 잘 기억이 안 나네요. 아마 드랍하라고 했던 것 같은데요. 어차피 총 개수의 에러 마진 한 10% 정도 두니까 몇 개 빠지는 거 이런 건 괜찮습니다. 아마 그러니까 IC9 코드는 있는데 텍스트가 없는 애들이 뭐 몇 개 안 될 거라고 예상을 하거든요. 만약 있다고 하더라도. 그래서 그렇게 뭐 한두 개 빠지는 건 괜찮으니까 뭐 드랍을 하셔도 되고 안 하셔도 되고 사실 뭐 그거는 뭐 원하시는 대로 하셔도 됩니다. 혹시 그게 몇 개나 되는지 알려주실 수 있나요, 재관님? 6,000개나 된다고요? 어드미션 CSV에서 어드미션 CSV에 있는 HADMID 중에 디스차지 서머리가 아예 없으면은, 그러니까 애초에 그 순서가 디스차지 서머리랑 그러니까 카테고리 디스차지 서머리고 디스크립션 리포트인 애만 가지고 시작을 하는 거예요. 그러니까 애초에 그게 존재하지 않는 HADMID는 쓸 일이 없습니다. 방금 제가 말씀드렸던 거는 카테고리 디스차지 서머리가 있고 디스크립션 리포트가 있는데 공란인 경우 텍스트가 공란인 경우에 어떻게 하냐라고 물어보신 건 줄 알았는데 그건 아닌 것 같네요. 그러니까 애초에 HADMID 중에 카테고리 디스차지 서머리가랑 디스크립션 리포트가 없는 애들은 처음부터 취급할 필요가 아예 없습니다. 네, 시작점은 디스차지 서머리 리포트를 가지고 시작을 하는 거예요. 그게 이제 존재하는 HADMID들 중에서 이제 그 IC9 코드들이 있는 애들과 이제 결합을 해가지고 데이터셋을 만드시면 됩니다. 네네, 맞습니다. 네. 네, 애초에 시작점이 노트 이벤트입니다. 예, 그렇죠. 어드미션 뭐 추가 피처를 사용하고 싶으시면은 써도 되고요. 뭐 에스니시티나 뭐 랭귀지나 젠더나 이런 거 쓰시고 싶으면은 사용하셔도 되는데 그게 아니면은 네. 뭐 최소한의 뭐 피처만 사용하겠다 그러면 쓰실 필요 없습니다. 네, 좋습니다. All right, so I guess this is a pretty important question. So what Jaewon Lee asked is there are there so the total number of unique HADMIDs based on the admissions table is larger than the number of HADMIDs that have discharge summaries, and the number of difference between the two is about 6,000. And the question was that whether we should we should use all the unique HADMIDs where they do not where some of them, exactly 6,000 of them, don't have any discharge summaries, and the answer is no. So our starting point is the note events table. So if we only deal with HADMIDs that are associated with a legitimate discharge summary. So don't worry about the HADMIDs that do not have any discharge summaries. All right, I hope that answers the question. 또 다른 질문 있으신가요? 안성용님, 클래스 업무 와이 트레이닝 계속 오늘 정상이고 제 기준 테스트 파일은 테스트 파일이 400, 트레인 파일이 1.6기가가 나왔다고요? 지금 한 로우가 몇 캐릭터가 나오죠? 지금 한 10,000클래스 정도, 다 합해서 10,000클래스 정도 된다. 그러면은 0101이니까 1바이트고, 그럼 10,000바이트고, 컴마 세퍼레이티드니까 20,000바이트고, 죄송합니다. 네, 다시 그 컨티뉴 하자면은, 그러니까 한 줄에 2만 바이트가 나온다고 치고 HADMI 제외하면은 커마 세퍼레이티드 클래스 커마 세퍼레이티드 0101이니까 2만 바이트고, 아 클래스 18,000개. 그럼 이제 18,000개면은 36,000 바이트네요. 한 로우가 36,000 바이트고, 그 다음에 총 몇 개 로우가 있죠? 뭐 대략 한 4만 개쯤 있나요? HADMI가 총 몇 개인지 모르겠는데 한 4만 개쯤 있다 치면은 36,000 곱하기 4만 바이트 하면 얼마입니까? 그러면은 1.4기가네요. 아니 그렇게 크다고요? 1.4기가라고? 한 10kg 메가 기가. 그러게 1.4기가쯤 되네요. 트레이닝이. 아, 요거 혹시 압축하면 얼마쯤 되나요? 탈볼 건집을 압축하면요? 혹시 압축은 아직 안 해보셨나요? 압축을 해도 1기가 안 되면은 그 KLMS에 올릴 수 있는 최대 용량 1기가거든요. 그래서 그게 안 되면은 그냥 조교분들한테 이메일로 보내시면 됩니다. 저번 프로젝트 1에서도 용량 초과 때문에 이메일을 보내신 분들 몇 분 계신 것 같은데, 네, 비슷하게 하시면 됩니다. 이게 1.4기가나 될 거라고 미처 생각을 못했네요. 네. 네, 좋습니다. It's a good question. Those are the errors I got. Precision score. Invalid value encountered in true divide. Only one class present in Y true. Not really sure what's happening here. Maybe your Y true and Y prediction have a different structure. Maybe one has one. Maybe one is like one-dimensional input and the other is two-dimensional input. So I guess you can ask the question in class. I'm not really sure. Yeah, thanks. All right, I think we should get started with today's material actually. 혹시 또 다른 질문 있으신가요? 네. All right, if not, I guess we can get started. All right. Actually, it's not that much of a big. We don't have too much to cover regarding the size of the material. So I guess we can get a bit. I can answer maybe one or two more questions if there are questions regarding project number 2. If not, we're gonna continue with the material. I thought, if I remember correctly, the deadline for project number 2 is 20th. Is that right? Was it 20th or was it 18th? I think it was 18th. Project 2. Yep. Okay. So it's 18th. So we have about exactly 1 week. All right. So 1 week. We have 1 week. I'm gonna. I expect this not to be too much difficult. Like since everybody has done project number 1, project number 2 should be easier actually because there's less amount of pre-processing to be done regarding joining the tables and all that stuff. I mean, there are still some amount of pre-processing to be done regarding how to pre-process the text. Like whether you should have a threshold for the length of the text, or how you want to stem them, how you want to normalize them. If you want to how you want to treat the numbers and that kind of stuff. But besides that, I mean, those are just NLP stuff, and there is already an NLP class going on this semester, so maybe you can get some tips from that class as well. So hopefully it's not that difficult for everybody. All right, let's get started. So this week's focus is medical image, and we are going to look at different types of medical images, because when we say medical images, we just kind of imagine x-rays or CT scans, but those are not the entire picture. There are a lot of medical images, and actually like medical videos as well. So we're going to look at different types of medical images first, and then we're going to discuss image classification and then image segmentation. So today it's going to be mainly the top two. So different types of medical images and image classification. Image segmentation will be, we'll cover that the next class in Thursday. And image generation, if anyone's interested in that, will come later in synthetic data in I think that was week 12 or something, according to the syllabus. So image generation can be, it covers a lot of ground. I mean, it covers a lot of applications. So purely just, synthesizing images using GANs is one thing. You can totally do that, like, using style GANs or that kind of stuff. You can actually generate a high resolution medical images or pathology images, or, like biopsy slides. You can totally do that. But you can also use it for other purposes, you can try to project what you would look like after plastic surgery. So for example, when you are interested in getting a plastic surgery, you go to a clinic. 성형외과에 가시죠. So when you go to a clinic, and then there's someone called 실장님. It's not usually the doctors. Someone there's like a manager, and then they consult. They are the consultants. So you go to them and you talk to them, like you want your nose fixed, you want your skin something, you want your eyes like bigger or wider or whatever. Like you have your own preferences, and then it would be convenient for you if there was a program that would actually synthesize an image of yourself, but with after the plastic surgery, after the surgery. So what you would look like if you done this or if you done that, something like that. So there is actually a simulator that actually does that for you. So that is a pretty big market. Like if there are some like software vendors or software developers that only focuses on plastic surgery simulation. So you can totally do that. That is an image generation. That is a part of image generation. So you take picture. So the managers, the clinic takes a picture of yourself in multiple dimensions, in multiple angles, and then upload that to the program, and then the program will reconstruct a facial image of your, like a 3D face image of you, and then they can start simulating different types of surgeries. The same goes with breast reconstruction for like cancer patients. So especially for female patients who have undergone a surgery to remove cancer cells of let's begin with the cancer type first. So the female patients, they often get breast cancer. 유방암에 걸릴 수가 있죠. Then if that's the case, then they need to remove the cancer cells from the breast. So it's like a breast cancer removal surgery. So after that, they would probably missing one part of the breast, or maybe both sides of the breast, and then usually they undergo a breast reconstruction surgery. So in that case, there is also a demand for a simulation program as to what you would look like after the breast reconstruction surgery. So if there is already a program, I think I've heard that there already exists a program that does this for you, like breast reconstruction, like how you would look like after this surgery. So those will be like different applications of image generation, which we will cover in week 12. I'm not going to cover like how you can do plastic surgery simulation. That's not that's not the main focus of this class, but it's just just one fun application of image generation. All right, so medical images. we're going to look at the different types of medical images. So anything that can be represented with pixels is just medical images, because there are a lot of different types of medical images. So chest X-ray is what we probably have most often, like it's the most abundant, most popular image type of image in medical images field. Actually, let me mute everybody. All right. Oops, sorry about that. Right. So yeah, as I said, it's the most well-known, it's the most frequent or rich source of medical images out there. And there are actually a lot of open source images for chest X-rays. So Mimic actually has a chest X-ray dataset called Mimic CXR, Mimic-CXR, which we're going to talk about at the end of the class today, because project number 3 will be using Mimic CXR. So chest X-ray, as I said, like there's a lot of like big, large scale open source data set for chest X-ray, not just Mimic CXR, but also there's something called Chexpert. So that's CHEXPERT, Chexpert. And I think that was released by the NIH. So NIH is a National Institute of Healthcare or National Institute of Health. So it's like the largest government-funded healthcare research institute in the United States, and I'm not sure what's the equivalent organization in Korea. 보건 의료. 그러니까 미국 한국말로 따지면 보건연구소인데 보건 의료 연구소 뭐 이런 건데 한국에 그런 게 있는지 모르겠네요. 근데 이제 NIH는 미국에서 이제 가장 큰 그런 보건 의료에 대해서 연구소라는 연구 집단인 굉장히 큰 연구소입니다. 그래서 거기서 이제 어떤 이미지들 다 모아가지고 체스트 엑스레이 이미지를 모아서 이제 오픈 소스를 해서 이제 수십만 장의 이미지가 그 데이터셋에 있습니다. So as I said, it's a large scale. It like typically consists of like hundreds of thousands of different chest X-ray images, which is more than enough to train a large classification model or generation model or whatever. All right, so that's chest X. Chest X-ray looks like this, but as we will see at the end of the class, there are a lot of different views of X-rays. Like you can take if you remember what you've gone through when you went to the hospital and took an X-ray, you actually sometimes you stand up, sometimes you turn your backwards you turn your front towards the X-ray image machine, or maybe you turn your back towards the machine, or you stand sideways. So it's like different multiple views, like frontal views or lateral views. And sometimes you lie down on a slate, and then they they take a picture of yourself while you're lying down or while you're like face up or face down. So there are a lot of different views in chest X-ray. So that's also a topic that could be interesting. All right, moving on. So CT scans. So CT images are also pretty well known, and there are some open source data sets for CT scans as well. And CT scans typically are actually 3D images. So it is not just a still image. It's not just a 2D image. It's actually a set of 2D images or sequence of 2D images where you can use those sequence of 2D images to reconstruct into 3D images, because CT scans actually go through this kind in order to take CT scans or to get a picture, the patient needs to go through this kind of donut shaped machine. So there is a X-ray machine here inside this donut shaped ring. Inside this ring there is a X-ray machine, and it can it's like taking a slice of your body. So X-ray slice of your 3D body. So there's like x-axis and y-axis, and then there's a z-axis. So z-axis being across this dimension here. So you can see that the images change shapes as you move into the ring. So like for example, I would say this is the end of your abdomen. This is like the beginning of your abdomen, because this is thicker. It's like more rounder. So it's probably your chest area. This is probably your chest area, and this is probably your like lower belly. Maybe. I'm not really too sure. I'm gonna assume this is liver and this is kidney, but I'm not too sure. But anyway, you can think of like this image moving along the z-axis. So if anybody has already taken a CT scan while in hospital, they are pretty familiar with this machine. So it is, CT scans are used for it's really useful, like it's really good for detecting cancer cells, or like whether it has spread to different organs and that kind of stuff. And so CT scans, you can take, it is useful for taking the entire image, 3D image of your body, starting from like the start of your abdomen or your lower belly, and then all the way up to the neck. So your entire like torso and belly and lower belly, right before your leg starts, entire image can be captured, entire organs can be captured, because all your organs reside between your neck and your leg, or in your belly. So while using CT scans, you can take the entire image of your internal organs. MRI scans. So MRI scans are also actually 3D images. So it's also a scan. It's it takes a slice of your body along the z-axis, and usually it is good for taking brain images. So with CT scans, I'm not sure if there's like a brain CT, but there is definitely a brain MRI. So it is good for trying to see if there's something wrong with your brain, or if there's like a brain tumor, or like something like that. So in order to take MRI scans, you also need to go through this kind of like donut-shaped ring, but this machine is way bigger than the CT machine. So CT machines is a bit lightweight. It's like the ring is smaller. It's like slimmer, but compared to like the thick machine here that we're seeing right now. But still, you still need to lie on this plate, lie on this bed, and then you slide through this gigantic machine, and you have to like sit really still. So taking a CT scan, it takes like really, I don't know, it takes about like a couple minutes or something like that. It's relatively a short amount of time. But if you but taking MRI scan, it takes a way longer time, like between like, I don't know, 30 minutes or like 40 minutes or something. During that considerable amount of time, like 30 minutes, you have to lie really still. And it's like, some people suffer from this because like they're either claustrophobic or something. So 이제 폐쇄공포증이 있으신 분들은 들어가서 30분 동안 가만히 좁아 터진데 이렇게 딱 가만히 누워 있는 게 이게 쉽지가 않거든요. 그래서 이제 MRI는 그렇게 뭐 자주 찍진 않습니다. 그리고 뭐 돈도 많이 들고, 요게 이제 그 초전도체 이용해가지고 자기 공명 일으켜서 막 돌리는 거래 가지고 전기도 엄청 듭니다. So it consumes a lot of electricity. So it takes some. As far as the cost is concerned, MRI scans are way more expensive than CT scans, and because it is using magnets, you cannot have anything metal inside your body. Otherwise, it'll just shoot out of your body and then get stuck to the machine. I'm not sure if you've seen like some weird photos in the internet where like chairs or like some kind of like metallic objects are stuck to the MRI machine, because it uses a superconductor, 초전도체를 이용하니까 이제, which is like a super strong magnet. So if there's something metallic around the machine, it'll get stuck to the machine, which can cause a catastrophe, like major catastrophe. Anyway, MRI scans, I'm going to assume the MRI scans are rarer compared to CT scans because, as I said, the cost and the amount of time required to take the image, but it has its own purposes. So there are, if I remember correctly, there are some like very small scale MRI scan open source data sets out there. So if you're interested in using MRI scans for one of your like research projects, then you can definitely look into that. So these three are probably the most well-known medical images out there: X-ray, CT scans, MRI scans, and then there are other images such as like here angiogram. Angiogram is 이건 이제 혈관 조영술 같은 거죠. So if a doctor is interested in your bloodstream, your blood vessel, then they inject into your body some kind of chemical so that can highlight the bloodstream and thus therefore the blood vessel themselves. So if there's something wrong with your blood vessel, or they've done a surgery on your blood vessel and then they want to see if it's going all right, okay or not, so they would take angiogram. And angiograms can be a video. Actually, it's not just a still cut image, but it could be a video, which is again it's a sequence of images, but in a different manner. Like CT scans and MRI scans, they are 3D images, but they are 3D images in actual literal sense, 3D-dimensional, because like there's a z-axis. But angiogram, if you take a video of the angiogram, then it's a sequence of images, but it is just a sequence of 2D images. So it's not, you cannot reconstruct it into 3D forms. It's just a, like the third axis is not a z-axis. The third axis is the temporal axis. So that's the difference. But it could be, as I said, it could be a still image, it could be a video, and you can actually try to segment the bloodstream, segment the blood vessel using the angiograms. Biopsy, this is also another, this is another major subfield of medical images, biopsy or pathology. So when you go to a hospital and then they perform a biopsy on you, 이제 생검을 한다는 거죠. 그러니까 이제 뭐 조직 검사를 해서 위내시경을 했는데 거기에 뭐가 있어요. 그래서 그게 이제 암세포인지 아닌지 궁금하면은 뭐 용종이 있는데 그건 이제 용종이 있으면 암일 수도 있잖아요. 그럼 이제 그거를 내시경을 하면서 이제 떼어내죠. 그 용종을 이제 톡 튀어나온 어떤 그런 생긴 거를 딱 떼어내는데 그 떼어낸 거를 이제 이 뭐라 그러죠? 이 조직 검사를 하는 거예요. 이게 이제 암 조직이냐 아니냐에 따라서 이제 당연히 향후에 어떤 경로가 바뀌니까 어쨌든 그래서 뭐 대장 내시경 할 때도 그렇고 위내시경 할 때도 그렇고 뭔가가 있으면은 거기서 띄어가지고 이제 그거를 조직 검사를 합니다. 그래서 그 조직이 이렇게 생겼을 수가 있는데, so as I said, when you go to a hospital to do like a medical checkup, then you 내시경 영어로 뭔지 모르겠네요. So when you put like a really small microscope inside your esophagus, so it goes through your throat and then reaches your gut, and then it just scans around to see if there's anything wrong with your gut. Your 위도 영어인지 모르겠네. 한 영어로 그냥 것인데 이제 뭔가 이 gastro 뭐시가 있을 텐데 하여튼간에 so there is, I guess someone's gonna endoscope. Yeah, actually, endoscope. Thanks. So yeah, when you perform an endoscope, then sometimes the doctors might find a nodule or like a small irregularities inside your gut. So they would take them out and then do a biopsy. So they slice it in. So they put it on a slide and then would do some kind of processing to highlight some different parts of your cell. So it's like using like different dyes, and then when you put the slide under the microscope, you would see an image like this. And then with machine learning, we would like to detect if there's a cancer cell here in this image or not. So detect or segment if there's if there's a cancer cell, then we would definitely want to see segment the area of the cancer cell as well. So this is a major area in medical images. So, and typically the problem with this is typically the biopsy, this kind of slides, they are super high resolution, I don't know, 4,000 by 2,000 pixels or something like that. So, so if you try to input that kind of size of image into a ConvNet, then your VRAM would blow up. So, but if you decrease the resolution, then you're going to lose a lot of information due to the reducing of the resolution. So you have to find a nice way to how to retain the image quality while not blowing up the VRAM. So biopsy or pathology is a major sub area. Skin photos is also another example. So it's just a photo of your skin and that's it. So it doesn't require fancy devices or detection machines, but it's just a kind of a magnifying scope put on your skin and that's it. So this is usually used to detect whether you have a skin cancer or not, which we'll look at today. And then the fundus photo, which is 망막 사진. So when you go to the eye clinic or eye doctor, or when you go to the eye doctor and then they try to find whether something is wrong with your eyes or something, then you would sit on a machine and then they would take a photo of your fundus, 망막 사진을 찍어가지고 이제 여기에 뭐 혈관이 막혀 있는지, 뭐 시신경이 눌려 있는지 이런 것들을 볼 수가 있습니다. And these are pretty much like very healthcare specific images. So you don't take this kind of images unless you go to a hospital or go to a clinic. But theoretically, anything could be healthcare or medical images. So there are applications like this even today. So when you have a home camera or home camera or home video, like a surveillance system inside your home, using like Nest or some kind of like Google Home or whatever. Like there are a lot of like smart home gadgets these days. So there must be like a video surveillance thing as well that you install. And then if you are a senior, or not even like just if you live by yourself, like if you live by yourself and then you somehow experience like a stroke or whatever, you fall down and then you don't get up, then the surveillance camera or the home camera will actually detect that you are staying still for like long enough amount of time. Then they will just they will ring 911 directly for you. So it is especially useful for like seniors who live by themselves. So like when they fall down, they might still be conscious, but they can't get up because they broke their hip bones or they broke their legs. So, and they're out of. So in that case, the surveillance system or the home camera can call the cops or call the hospital instead of for you. So this is actual application that is being sold as of today. So in that case, you need to have a video. So in this case, the input to the model would be a sequence of 2D images. So it would be a video. And then when you see, and you need to classify whether there is something wrong with the person or not, based on the movement of the person, like whether they fell down or whether they are like, limping, like, 다리를 전다거나, or whether just, they are standing still and not doing anything or whatever. Like if there's anything anomalous happening to the person, then the machine will have to pick that up and then call the hospital for you. So that could be another, subfield of medical images. But this is more like healthcare rather than clinical. All right, so those are different types of medical images. And any questions so far with the images? So these are different applications or different application in terms of machine learning. So in machine learning perspective, I've categorized the different applications or different machine learning approaches for medical images. So the first is obviously classification or regression. So given an image, perform classification or regression. So given like 2D or 3D images, doesn't really matter. Just given given pixel input, try to just perform classification or regression. And so pathology would be one, or disease or diagnosis, like disease classification. Like given a chest X-ray image, try to classify whether this image is whether this patient has pneumonia or whatever, like pneumonia or tuberculosis, that kind of stuff. So or if it's just a normal chest X-ray. So that would be just multi-class classification, or actually it should be multi-label classification, because you can get 2 or more diseases at the same time. Bone age prediction would be a regression problem. So given like a bone image, like hand bone or whichever bone, you try to guess the age of the patient, of the individual whose X-ray bone we're seeing using the image. So I'm not really sure what kind of application, what kind of real world application this might be, but there is actually a challenge, or either on Kaggle or some open source dataset, trying to guess the image of the bone of the owner of the bone. So maybe if I have to imagine, maybe if there's like a murder case and there's nothing but like just bones remaining after a long amount of time, then your bodies would also already have been decomposed by that time, and then there's nothing left but the bones. So you would have to like guess the age of the person, of the murdered person by the looking at the bones. So maybe that's the reason why we do this kind of stuff. So the second one is the segmentation. So we can do this for pathology images to try to segment the cancer cells, or you can do this for like internal organs. So when you take a CT scans, there are a lot of different organs packed into your body. So you might want to segment different types of organs like livers, heart, kidney, pancreas, that kind of stuff. So it will be multi-organ segmentation. Sometimes you have to you perform like teeth segmentation with with your jaw images as well. So that is also a like particular example. Or you can do a image processing. This is actually computer image processing rather than machine learning for computer vision, but it is still using a lot of machine learning techniques, such as improving quality, like increasing resolution, like super resolution, or removing noise or artifact of the image. Like if it was taken with like some noise, due to like using old devices or old machines. So trying to remove the noise or artifact is also another application. And I've put video and 3D images aside, but they actually are just part of the image segmentation. So if you look at a brain MRI and then you're trying to detect brain tumor, then you need to segment the tumor cells out from the other like normal cells. Or as using angiogram, you can try to segment blood vessels as well. So there are a lot of different approaches and a lot of different applications using medical images. I'm sorry. All right, so let's get back. All right, so these are the introduction to different types of images and applications. And today we're going to talk about disease classification in specific. So as I said, image segmentation will come Thursday. So today is just basically classification. And typically it's just direct application of confidence. So input is just 2D image and output is disease classes. So it could be binary, it could be multi-class, or it could be multi-label. The output is just, good old classification. So there's nothing new here. It's just people have been using machine learning. People have been using confidence for image classification since the ImageNet challenge. So using this for medical purposes is not too much different. Sometimes you use medical domain knowledge, or sometimes you don't, and that's probably the only difference. So some of the well-known works of disease classification are these three. So diabetic retinopathy detection in from Google's 2016 JAMA paper, skin cancer detection from Stanford's 2016 Nature paper, and breast cancer screening from Google's 2019 Nature paper. But there are probably millions of medical image papers out there, and these are just the ones that are well known because of all the promotion and advertisements. Google has a lot of money, so they can advertise their work using a lot of media. So these are the well-known works, but probably these are not the best works out there, because I can't decide which one is the best, because among the like million different medical image papers. But these are the well-known works, and they are pretty solid in my estimation. And for those who are not familiar with JAMA paper, JAMA is probably, I'm not sure if it has the highest impact factor, but it is one of those journals that has like really high impact factors, like 40 or 50 or 60, something like that. So anything that is so JAMA is like journal of, I'm not sure what this is abbreviation for, but it's a medical journal, and this is probably there are two well-known medical journals out there, which is one is JAMA and another is New England Journal of Medicine. So that's NEJM, New England Journal of Medicine. So those two are like the top two medical journals. And if your paper is in either JAMA or New England Journal of Medicine, NEJM, then it means that it is usable from next day. So it has already been clinically proven that your work works. It's legitimate. So it, like all the other doctors in the world, they can trust your work in JAMA or in EJM, and then they can apply that work for their practice. So it has that amount of like prestige and authority. So getting your paper in JAMA is like it's like getting your paper in Nature or something. So Google has done that in 2016 using machine learning for diabetic retinopathy detection using fundus photographs. And it is, not too surprisingly, just purely confidence-based approach. So it is trained on about 130,000 fundus images graded by 54 ophthalmologists. So ophthalmologist, just a fancy name for eye doctor. So graded by 54 US licensed eye doctors. So there's just a lot of annotators. And graded means that, different, just labeling. So the model is evaluated on 10,000 images, each graded by at least 7 eye doctors. So training set was graded or labeled by 54. Test set was labeled by 7 eye doctors. And interestingly or surprisingly, the performance of the confident was on par. So it's similar to human doctors' performance in terms of AURC. So human doctors here. So the evaluation set was graded by 7 eye doctors. So it means that on par with, on average, 7 human doctors in terms of AURC. So image grading, what does the grading mean? And the fundus photo, we've already seen fundus photo a couple slides ago. So this is fundus photo. And when the eye doctors grade or label the images or annotate the images, they grade in three categories. So one is image quality. So given a fundus photo, whether it is of excellent quality or good quality, adequate quality, or insufficient for full interpretation, insufficient for any interpretation, it's just different grades of image quality. And then they grade for 2 diseases. One is diabetic retinopathy. So that is in Korean. diabetic. 당뇨성 망막 염증입니다. 레티나가 망막이 맞나요? 레티나 망막인가요? 잠깐만요. 네, 망막 맞죠. 네, 레티나 망막, 그러니까 파티면은 이제 거기 아프다는 거니까 이제 뭐 망막증, 염증, 염증은 아니네요. 그러니까 이제 보통 ITIS 무슨 사이너사이티스 무슨 뭐 아르트라이티스 이런 게 이제 염증이니까 그 레티노파티면 이제 거기 아픈 거니까 그냥 망막증입니다. 그래서 이제 당뇨를 걸리면 보통은 여기저기 막 손가락 끝에가 뭐 손가락을 절단한다던가 뭐 이런 여러 가지 부작용들이 있잖아요. 발가락을 절단한다던가 이런 식으로. 그래서 그 망막에도 눈에도 문제가 생길 수 있어요. 당뇨가 걸린 사람들. 그래서 그거를 이제 당뇨성 망막증이라고 걸리는 거라는 겁니다. 뭐 그거랑 so that is one disease, and another is diabetic macula edema. So macula is 황반, edema is 부종. So it's some like swollen. 그러니까 황반이 부어 올랐다, 뭐 부종이 있다, 뭐 그런 거겠죠. 당뇨 때문에. So it's like swollen macula due to diabetes. So they grade how severe these 2 diseases are using this tool. So this is like on the right side is grading for diabetic retinopathy. So one is no DM, no diabetic retinopathy, no DR, and this is mild and severe and probably like proliferative. All right, so this is a grading tool. And as I said, there are about 130,000 sets of images were used for training and validation set. And the model was, after training the model, they evaluated the model on two different sets of fundus images. One is called IPEX-1, which consists of about 10,000 images, and another is Messidor-2, which consists of about 1,700 images. So that's basically it. There are a lot of details, but we're just gonna skip that. If you're interested in this, you can take a look at this later. And then the model architecture. So what they use is something called Inception version 3. So Inception is the work that first used batch norm. So, and the first batch norm paper was introduced in 2015. I'm going to guess 2015 or 2014. I'm not really sure. Maybe 2015. And that was Inception version 1. And after that, So it was obviously developed in Google, and so Inception version 1, and then they improved Inception until version 4, if I'm correct. So there's version 2, there's version 3, and there's version 4. And by the time Google people were working on this this diabetic retinopathy project, I think they had Inception version 3. So that was back in 2016. And Inception version 3 looks like this. So it's if you look at it, so a lot of people just use ResNet these days. So there might be some students who are not familiar with Inception architecture. But if you look at this, so this is the architecture, and the orange one is convolution, the blue one is average pooling, and the green one is max pooling, and yada yada yada. But the thing to note is that there is a repetition of modules here, like this module here, here. Like there are 7 repetition of this module called an inception module. So inception module consists of different kernel sizes, like 1 by 1 kernel, 2 by 2 kernel, like 3 by 3 kernel, 5 by 5 kernel, that kind of stuff. And in this work, they used a Inception version 3 pre-trained on ImageNet. So, and one of the characteristics of Inception model is that the fully connected layer is only used at the last time here. So after the global average pooling, after that they use fully connected to project this into like different number of classes. It's just like a penultimate layer for coming up with the logis. So before that, there is no fully connected layer whatsoever. So it means that it can process any resolution of images. So it could be 128 by 128, 256, doesn't really matter, because nowhere between the logit and the input there is no fully connected layer. So it doesn't. This model doesn't assume a fixed resolution input. So that is one of the characteristics. So this differs from the previous models, such as AlexNet or VGG16 or VGG19, which looks like this. Like it's just a couple of stacks here. Like there is no multiple routes like this. Like there's like one route here, here, but in VG16 or VG19, there is no multiple routes. It's just consists of 3 by 3 convolutions from bottom to the end, and there are some fully connected layers after the pool. So it doesn't use global average pooling. So it does expect some kind of like fixed resolution images input. So compared to this, this is Inception version 1. So the Inception module looks like, so in the Inception version 1, the Inception module looked like this. So from the previous layer, there are 4 routes. One is 1 by 1 convolution. Another is 1 by 1 followed by 3 by 3. 1 by 1 followed by 5 by 5. 3 by 3 max pooling, then followed by 1 by 1 convolution. So it's just trying to reduce the dimensionality of the image feature map, and then concatenating them. So there's concatenation here, and then concatenate them, and then you repeat this process multiple times, like 1, 2, 3, 4, 5, 6, 7, 8, 9 times. They repeat this 9 times. So this is the very first Inception version 1. And at the time, so this is 2014. So at the time, they actually won the ImageNet challenge. So that was before that VGG16 won, and before that AlexNet won. So, and it used a very small number of parameters. In Inception 1, they only used 5 million parameters. In Inception version 3, I think the exact number was 22 million parameters. So compared to like AlexNet and VGNet, the number of parameters is like 12 times less and 27 times less. So it's a very efficient model. Yeah, I've just already covered this, so I'm just gonna skip this. So yeah, this is a stack of Inception modules, and here there are auxiliary losses from time to time. So there is the same here's the output module. So there's like a global average pooling followed by logit layer. So there's the same thing here as well from time to time. So in the intermediate layers, this is just to help the model just learn better. So you're trying, because there's like a pretty high there's a pretty long sequence of back propagation from here to here. So sometimes you want to put the gradient signals from the get-go in the intermediate layer. So this is like you put the gradient signals directly into the intermediate layers, like injecting it like from the side and side. So there's like auxiliary classification loss, but they don't do this in version 3 anymore. So you don't see any side inputs here. You just have here, and that's it. All right, so yeah, inception version 3, and what they do with this is just 4 binary classification heads. So at the end, there are 4 binary classification heads, and there is one for moderate or worse diabetic retinopathy, and one for severe or worse diabetic retinopathy, and one for diabetic macular edema, one for fully gradable or not. So this 4th one is just to classify whether this image is useful or is usable for image classification or not. So that means it's gradable or not. So if your image is like not gradable, then or if the model decides this image is not gradable, then you can just reject them from the classification. So there are 4, as I said, 4 binary classification heads, and they are all evaluated by AUROC. So they're all like these are all different like binary classification, 4 different binary classification. And this is the performance plot. So this is the AUROC. And as I said, 2 different evaluation data sets. One called IPEX consisting of 10,000 images, another MESIDOR2 consisting of about 1,800 images. And here, this black line is the AURC curve of the inception model. And these dots here, the colored dots, are different eye doctors. So in IPEX, 8 doctors participated for labeling, and in MESIDOR2, 7 doctors. So you can count 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 color circles here, and there are 1, 2, 3, 4, 5, 6, 7 color circles here. So compared to human eye doctors, inception model is doing a pretty good job actually. So this is the curve, and there are 4 doctors that live outside, that are located outside the curve. So it means that it is outperforming the inception model. But here, there are 4 doctors that are inside the curve. So it means that they are underperforming the inception model. So that's why you can say that it is like on par, on average, showing similar performance to the eye doctor. And in this evaluation set, it is actually outperforming like there are only 2 doctors that live outside the AURC curve, and all the other doctors are either on the line or they're beneath the line. So in this data set, the model is doing a better job than, on average, 7 doctors. So it is a very reliable model, as long as you can procure a high quality like fundus images. So Google actually, so let me see. Yeah, so Google actually launched this model in India, if I'm correct. So once they wrote the paper, they tried to do this, they tried to clinically validate this model on like other countries and other parts of the world, and especially in India. And in some parts of India, they don't have a machine that can take a clear fundus photographs, and sometimes the engineers or the workers who use the machines to take the fundus photos of the patient, they don't know how to manipulate, or they don't know how to use the machines optimally to get how to use the machines effectively to get an optimal fundus photo. So like the photos might be dark, or it might have it might have artifacts, it might have noises, it might have different weird resolution. So in those cases, this model doesn't work at all. So that's usually the case of when you try to deploy your machine learning model in real world, because the inputs are not as clean and high quality as the training set that you use for training your model. So that's one of the lessons that Google learned when they tried to clinically validate the model in India. I'm not sure if it was India or Indonesia, or it was some part of like Southeast Asia. I'm I'm not really sure. I've read the article some time ago. All right, yeah. Anyway, so moving on. So next one is skin cancer detection by Stanford. So this is the second one that we're going to look at today. So we're not going to look at the breast cancer screening. So we're just going to look at the fundus photo and the skin cancer detection. So this is the work done by Stanford people, and the title says it all. It says dermatologist level classification of skin cancer with deep neural network. So it means that the deep neural network, especially confident here, shows on similar performance as the U.S. certified, U.S. licensed dermatologist. A dermatologist is in Korean is dermatologist is just a fancy name for skin doctor. 피부과 의사입니다, dermatologist는. So yeah. All right. So yeah, it was printed in Nature in 2016. Actually, these two works, this and this work, was printed in respectively JAMA and Nature about the same time, actually, like the end of 2016. And they both used Inception version 3 model. So I'm not sure why this is so. Maybe someone was interning at Google and then returned to Stanford and decided to use Inception version 3 or something like that. Or I don't know, they collaborated. I'm not really sure, but the approach is overall very much similar. So the Inception version 3 model was trained on 130,000 skin lesion images. 그러니까 이제 그러니까 피부에 병변이 있는 쪽의 이미지를 이제 이용해서 학습을 한 거죠. So 130,000 skin lesion images consisting of 2,000 different diseases. So there are a lot of different like subtypes of skin diseases, and their data set, their training set, 130,000 images, consisted of 2,000 different diseases. So, and then the model performs against 21 US licensed dermatologists for 2 binary classification tasks. One is carcinoma versus keratosis. Another is melanoma versus nevi. So this is carcinoma is the most common skin cancer, and malignant melanoma is the deadliest skin cancer. So it means that if you have melanoma, you're likely to die because of this. And compared to that, nevi is just, I'm not sure what nevi is, just like samagi or whatever, or some kind of like 피부에 뭐가 이렇게 반점이 났다거나 그럴 수 있잖아요. 그런 것들이 아닌가 싶어요. 근데 칼시노마랑 멜라노마는 둘 다 이제 피부암의 종류입니다. So let's see if you can decide whether one is malignant, one is benign. So one row is an image of benign diseases or benign neoplasms. Neoplasm 이제 그 종양이니까 이제 양성 종양일 수도 있고 그러니까 종양은 아니고 이제 스킨 이 피부에 뭐가 난 건데 하나는 양성이고 하나는 악성입니다. 근데 이제 뭔지 아실 수 있겠나요? 이게 양성이고 이게 악성인지 또는 이게 악성이고 양성인지 아실 수 있겠나요? To me, it was actually very confusing because I'm not a dermatologist, and it's really hard to decide which one is malignant and which is benign. I'm guessing there is no dermatologist here, so surprisingly, if it was up to me, I would say this is the malignant and this is the benign case. But actually, this is benign and this is malignant. So it is virtually impossible for me to decide which one is malignant, which one is benign. But surprisingly, Inception version 3 can do it as well as a U.S. licensed dermatologist. So what they do, first of all, unlike the previous work, they actually create a new skin disease taxonomy by consulting like dermatologists. So they manually construct a skin disease taxonomy because they first work with 2,000 different diseases, and they wanted to group these 2,000 different diseases into multiple classes. So that's why they come up with this kind of taxonomy. So in skin disease, there's like non-neoplastic. 그러니까 종양이냐 아니냐 해서 종양이 아니다. 비나인이면 이제 양성 종양이다, malignant은 악성 종양이다. 이렇게 이제 크게 세 브랜치로 나뉘고, 그다음에 이제 그 안에서 또 이렇게 브랜치로 나뉘고 그렇게 되는 거죠. So there are 3 major categories: non-neoplasm, and then benign neoplasm, and malignant neoplasm. And then there's like subcategories, sub-diseases. And they use this novelly created skin disease taxonomy to group the 2,000 diseases into 757 training classes. So basically, they train Inception model to perform 757 way multi-label classification. or actually, I think they do multi-class classification, because using just a small amount of, like this small lesion can only be one class at a time. It can't be multiple classes at a time. So they do 757 multi-class classification. So simply, they just put the skin lesion image into the Inception version 3, and then they perform 757 multi-class classification. And then when doing the final detection, the final inference, these here, like carcinoma versus keratosis, melanoma versus nevi, they group these fine-grained or granular skin disease classes they group them into carcinoma and melanoma, or nevi versus keratosis. So they group them. So they actually do a vote. So like if these if some subclasses of the training classes, if the sum of the if the total sum of the probability of subcategory, subgroup of the training classes like amounts up to like 0.5 or 0.6, then the model says, okay, so this person has carcinoma or not, something like that. So yeah, so here the training classes, 757 training classes, they each correspond to the edge, to the leaf nodes. So like there are 757 different leaf nodes here. And here, these inference classes, so the high-level classes, correspond to benign neoplasm or malignant neoplasm. So what the doctor actually are interested in is whether a given image or given lesion is malignant or benign. So that's probably sufficient. So this is a model performance. Again, this is on par with average board certified, so US licensed dermatologists, specifically 21 dermatologists. So if you count the red dots here, there would be 21 red dots. So actually, there are 25 red dots here. So different types of diseases: carcinoma, melanoma, and melanoma under better quality images, dermoscopy images, rather than just taking a photo. So dermoscopy it's a special device that takes like a high quality photo of this. So this is just taken photo by like photograph, like, just like camera, or probably not mobile phones, but some kind of like high resolution camera. But you can use a specialized devices called dermoscopy to get a better quality image. And if they do, you get like, in that case, the model outperforms most of the dermatologists. But in other cases, for melanoma, it's more or less the same. In carcinoma, the model has better. So the blue line, which is the AURC line, is actually covering most of the dermatologists. So the AURC is actually 0.996, so 96%, which is like really, really high. Right, so yeah, you can see that the average dermatologist locates here, here, and here. So in all three cases, the model is outperforming dermatologists. But again, as I said, if you deploy this in the real world and the input image is not as high quality or not as clean as the training set used for training this model, then the model would the performance would tank. But compared to that, humans would be very robust to like abnormal or anomalous input images. All right, so this is just a T-scene visualization. It means that the model can actually the model understands different types of disease, skin disease very, very, very well. So anything that is embedded here looks like this. Anything embedded here looks like these, and they all belong to a coherent, consistent disease category, disease class. So everything here is carcinoma. Everything here is melanoma. Everything here is keratosis. Everything is nevi, and so on and so forth. And this is a saliency map. So just using gradient descent to just calculating the gradients of based on the class. So it means that anything that is dark, so the darker dots have a higher influence in the final classification category. So you can see that it is actually focusing on the relevant pixel area as humans would do. So like if you have just one specific lesion, then the Inception version 3 would focus on that region. But if it's just scattered, it is if the lesion is covering a wide area, wide skin area, then salience of it would be also spread it out. So it's just, you know, just a way to indirectly say that the model is performing as human doctors would do, or hopefully as human doctors would do. All right, so this is the end of the two very most well-known works, and you can see that this is not too technically too advanced. It's just you have the important thing is to actually procure or gather a high resolution, like high quality images with very clean labels, labeled by specialists like eye doctors or skin doctors. So that is the starting point. And as long as you have a pretty solid model like Inception version 3 or Resonant or whatever, like WideNet, whatever, then this would work. This would show a very reasonable performance, sometimes even outperforming average doctors. So you can say that the models that have been developed so far are, you know, useful enough to do this kind of medical image classification. And obviously, well, I'm not a medical image expert, so there must be like million real like state-of-the-art works out there that tries to, you know, inject domain knowledge or tries to segment, or they tries to use only small amount of label data, something like, you know, very different, just trying to address different challenges in medical image classification. I think there was a chat question from 현지 황, 네, 황현진님. 13만 개 인풋 데이터로 760개에 달하는 클래스를 클래식했는데 충분히 잘 된 것이 충분히 없다는 생각이 드는 보통 인풋 데이터 클래스가 없는. 좋은 질문인데요. 뭐 그런 가이드는 딱히 없고요. 그러니까 지금 이게 잘 되는, 이제 아주 잘 되는 이유는 이 이미지들이 처음에 일단 760개 다른 클래스 클래스는 잘 되는 게 아니라 760개를 다시 모았잖아요. 케라토시스냐, 뭐 칼시노마냐, 뭐 멜라노마냐, 네비냐로 나눴기 때문에 이제 96%의 AUC가 나온 거고, 실제로 760개의 클래스를 나눈 거는의 성능은 저는 잘 기억이 안 납니다. 뭐 페이퍼 있는지 모르겠는데 760개를 가지고 클래스 해가지고 애큐리시를 쟀을 때도 96% 나왔다는 얘기는 절대 아니에요. 그거를 760개 클래스를 모아가지고 바이너리 형태로 만든 다음에 쟀을 때 AURC가 96%가 나왔다는 얘기입니다. 그러니까 실제로 760개의 멀티 클래스 클래시피케이션 애큐리시가 뭐 50%도 안 나올 수도 있겠죠. 어쩌면. 네. 혹시 잠깐만요. 제가 잠깐 찾아볼 수 있을까 싶네요. 봅시다. Secondly validate partition. 그래서 760개에 대한 애큐레시를 리포트를 안 하는 것 같네요. 760개는 아니고 요 그림에서 이제 여기 바로 아래가 이제 레벨 1이라고 치면 이 세 개가, 레벨 2는 이제 9개가 있대요. 여기 뭐 그림이 다 나오진 않았지만 레벨 2는 9개가 있는데 9개의 클래시피케이션 했을 때 애큐리시가 대략 55%가 나온다고 합니다. 그러니까 이제 막 엄청 잘 되는 건 아니죠. 9개를 클래시피케이션 하는데 55%가 나왔다는 거는 그렇게 썩 잘 되는 건 아니죠. 근데 이제 그거를, 그러니까 여기서 핵심은 바이너리로 그러니까 클래스들을 뭉쳐가지고 지금 이제 말리그넌트냐 아니냐로 뭉쳤을 때 그때 AURC가 96%가 나온다는 겁니다. 그래서 아마 760개 전체 다 했을 때는 뭐 애큐러시가 뭐 40%도 안 나오지 않을까 싶습니다. 근데 어쨌든 간에 이게 그나마 잘 되는 거는 이미지가 다 정형화돼 있잖아요. 일단 다 사람의 살이고 피부고, 그다음 그 가운데에 딱 그 어떤 뭐 점이나 어떤 뭐 사막이나 아니면 뭐 암세포가 있고 딱 정형화돼 있으니까 이제 13만 개 가지고도 충분히 그게 잘 커버가 되는 거예요. 이 스페이스가. 그러니까 이게 만약에 뭐 이미지넷이었으면 막 뭐 개 사진도 있고 뭐 자동차 사진도 있고 막 무슨 들판 사진도 있고 막 그러니까 이 변수가 엄청난데 이건 지금 딱 사람의 피부고 가운데에 어떤 병변이 있고라는 그 정형화된 이미지가 있기 때문에 13만 개 가지고도 충분히 학습이 잘 될 수가 있습니다. 네. 네. Alright. So we are almost out of time. So we're just going to briefly take a look at the Mimic CXR dataset. So Mimic, as I said, there are two well-known chest X-ray large-scale chest X-ray open source dataset. One is Mimic CXR, and another is CheckSpurt by NIH. Obviously, Mimic CXR was open source by MIT people. And let's see. So Mimic CXR is large-scale chest X-ray image report dataset. This is a very attractive dataset because it contains both image, the X-ray image, and also the free text note, the report. 이제 그 방사선과 가지고 이제 체스트 X-ray 찍으시면은 X-ray를 찍고 끝나는 게 아니라 거기 있는 이제 선생님이 옆에다 이렇게 뭘 소견서를 쓰거든요. 이제 뭐 폐에 뭐가 있는 것 같다, 뭐 희끄무린 게 꼈다, 뭐 심장이 커진 것 같다, 뭐 한쪽 폐가 찌그러졌다, 뭐 이런 걸 쓰신단 말이에요. 이제 그런 거가 같이 있는 거예요, 이 데이터셋은. 그러니까 첵스퍼트라는 거는 텍스트 리포트가 없거든요. 이미지만 잔뜩 있는데 얘는 이미지랑 프리 텍스트 노트가 같이 있기 때문에 이제 멀티모달 러닝을 하거나 뭐 컨디셔널 제너레이션을 하거나 이럴 때 아주 유용하게 쓸 수 있습니다. So as far as I know, this is the only large-scale dataset which contains both images and free text notes. So it's a very attractive dataset for doing multimodal learning. So it consists of about 227,000 studies. And so I'm saying studies because each study has corresponding notes. It is missing some notes, but basically each study could consist of one image, or it could consist of two images or three images, but it always comes with a single note. So for example, here, this is patient numbers 1000032. So this is a single patient, and this patient has gone through 1, 2, 3, 4, 5. No, 4. So 1, 2, 3. Yeah, this patient has gone through 4 studies. So study 504112667, and it has 2 images with 1 note. Another study has 2 images and 1 note. The third study has 2 images and 1 note. And the fourth study has only 1 image and 1 note. So as I said, when you take X-ray, you can take like frontal view, like lateral view, like a back view, or sometimes you lie down, you stand up. So there could be multiple views or multiple images per study. But for one study, there can be only one summary of your or one report. So that's the relationship between the number of images and number of reports. So unfortunately, this patient ID here is not connected to the Mimic 3 dataset. Not yet. So in Mimic 4, they are planning to connect or link this patient ID to the Mimic 4 dataset. So in that case, then you can actually do a lot of interesting stuff with structured codes and unstructured codes and other free text notes with images. But until before that, we can't do it yet. So okay, so this is Mimic CXR. So it has a lot of images. Like it has like 700, approximately 400,000 images. So this is really more than enough to train a really powerful classifier. Yeah, so as I said, there are multiple views, and it has multiple diverse aspect ratio as well. So views, like this is a frontal view, this is the lateral view, and sometimes this is like, I don't know, this is like 90 degrees rotated. And the ratios are, it doesn't come with a fixed ratio. It could be like horizontally wide or vertically long, or it could be a square shaped image and all that kind of stuff. And sometimes the private information is inside the image themselves, so it is masked like this. Like there's like a black mask here. So because this probably has like dates or names on this image, so that they're masking this. And the reports, so the reports usually have templates. So it's it looks like this. So there's like examination. So there's like a subheadings, and the subheadings are divided by a blank line. But So they start with examination, indication, technique, comparison, and then usually, typically, interesting information are usually stored in findings subsection and impression subsection. Findings is like the summary of what the doctors think about the X-ray image, and impressions are like, kind of like final diagnosis. But this is just a recommended template. So the doctors don't usually have to follow this to the letter. They can add new subsection, or they can delete subsection, or they can just ignore all this template and just write a long free text note as well. So that's also something to consider when you use this data set. And obviously, private information is hidden. So like the age of the patient, or the name, or the exact dates, they're all like, masked using this using some kind of like special way to mask them. So that is the original Mimic CXR, but there's also a derived data set called Mimic CXR JPEG. So Mimic CXR JPG. So it's an image report data set completely derived from Mimic CXR. So there's nothing virtually different between the two. Like as far as the number of images and number of reports are concerned, they're exactly the same. But this one consists of image and structured labels. So images are no longer originally these images are stored in DICOM format. So DICOM format is like a format that is used by a lot of most hospitals when they try to store like radiology images. So this DICOM format is like a radiology image format. But in this JPEG dataset, they converted that DICOM format into JPEG format. So same number of images, but in JPEG format. And each image, or each study is associated with multiple labels. So it's a multi-label data set. So how they came up with the multi-labels per study is they used a text processing tool called Chexpert and NegBio. So labels are derived from the original free text node. So there are nodes. So they applied a text processing tool called either Chexpert or NegBio, and applied it on the free text node to come up with 14 different labels. So, and 14 labels they can be represented in 3 different forms: positive labels, negative labels, and uncertain labels. So in total, each study is associated with 42 different labels, or 42 dimensional output classes. Yeah, so that's the only difference between the CXR and the CXR JPEG. So if you're interested, if you only want to do image classification, then you might as well just use Mimic CXR JPEG instead of Mimic CXR original, because in JPEG, they already have the labels for you. So actually, project number 3 will be using Mimic CXR JPEG, because project number 3 is automatic diagnosis. So just medical image classification and multi-label classification. So given an image, perform multi-label prediction into these 14 different labels. And the further details in the specs will be shared in week 14 as per the syllabus. But if you're interested, you might want to get familiar with the Mimic CXR JPEG dataset. Earlier the better, since you already have access to this, because if you have access to PhysioNet, then you have access to everything inside PhysioNet. So you can actually explore what the dataset looks like, and then maybe do a bit of a EDA on by yourself. All right, so any question with the Mimic CXR dataset? Nope. All right. We're going to talk about this again anyway in week 14. So I guess that's fine. All right, everybody. Thanks for coming, and I'll see you guys this Thursday. Bye-bye.